3, 2, 1, 0.
Success! So this project was inspired by some friends that we had over to watch a rocket launch of a nearby Air Force base that fires rockets here locally at night. And it turned out that the mission was scrubbed several times. And so we decided then that we're going to have our own rocket launch. And so I started looking into model rocketry and that sort of thing online, and was really impressed with how far it's come. It turns out my wife actually used to fire these off when she was a kid with her father, and so we both thought it would be fun to try it. I've never done it before, and thought, well, how can I apply the Arduino to the model rocketry? And that's basically what I've done here is I built a data logger using an SD card and an altitude chip, a BME 280 chip that will log the altitude that the rocket fires into and then write it to the SD card. This little module here is a knockoff of an Arduino Leonardo, but it's a micro mini one, and so it's very, very small and it's very lightweight. That's the key for all of this, really. So I actually thought that that would be a lot of fun. And so that's a good project to code some Arduino code and log it onto the SD card as this thing fires up into the air, and then take the data from the SD card and put it on the laptop and do a graph of it showing how high up and how long it took in milliseconds for the rocket to go up in the air and then come back down. And so that's what this project is all about. Now, I'm not going to give you all the background information on the model rocketry. I'll show you a little basic stuff here that I've kind of learned, and then you can look online and play with it more yourself. I'm going to focus mostly on the data logger code and the Python code I use to graph it. And I also have some websites I want to show you that I devised a bunch of notes from, and show you where I bought certain items, such as this module and that module and the hardware for this. And that's basically what I'm going to show you. It's going to be just a rough introduction, but it'll be enough for you to get started. And if you want to make bigger rockets that are 3 feet tall, or whatever size you can. So let's go ahead and start with the basics. This is the rocket engine. This is the actual rocket. You buy it from Estes. They've been around for a long time, and they're very well known, and their product is very stable. These rocket engines come in different sizes. There's nomenclature, alphanumeric number here that tells how many seconds it burns, how high up it flies, that sort of thing. But I'm going to start out more simple. Also, the color of the rocket engine printing here also has a specification, but I'll get into that later. Right now, let's just look at the rocket engine. Basically, it has one port where the exhaust comes out. It's a ceramic plug, and then at the top it has a solid ceramic plug, and this goes up inside the rocket. And when the fuel is spent, it hits a small charge that blows this cap off, which then jettisons out the nozzle, deploying a parachute, which you can see here. So, and then the thing comes back down to ground, and you take the engine out and put a whole new engine in and redo the whole thing. But let me start with how you actually install the engine. So the opening goes down so that when the rocket takes off, it can actually have the thrust coming out. You don't want to do it the other way, obviously. And so what you use are these little things called igniters. This is an igniter, and you put it into the hole as far as it'll go. You don't need to push it. And then you take these little plastic plugs. It's a little, there's a yellow and pink. This size requires pink. The C-size engine requires a pink. And then you take it and you put it in like that. Whoops. And there we go. And that holds the igniter in. And I always suggest moving these out a little bit so that when you clamp the control unit, it's a little battery operated control unit, you clamp it here and here, and that will allow you to fire off the igniter, which will set the powder off. Now I always recommend bending this over so that it's away from this tube. This tube goes on these rods. Now these rods are vertical. They go vertical like this, and then the rocket engine goes over the rod like that and then fires off into the air. Well, the rods that come with the kit are multi-segmented and they're kind of flimsy, so I don't use that anymore. I went out and bought a solid core rod, and I've lubricated the rod with Teflon so that it's smoother, but it's solid core, and that works a lot better. And it's also a larger rod, so it's stiffer, and that gives you a better flight. So now that you have the igniter in and all this, you want to pack in the parachute. Well, you can't just pack it in any old way. You need to take what's called wadding, and it's like tissue paper, but it's slightly fireproof, and you pack it in here like this. And what that does is that prevents you, and you poke it way down, that prevents the explosion from burning the wire, the little pieces of string or your parachute. So you need this wadding for sure. I also add a little extra wadding into the nose cone because I have had on occasion where the parachute gets driven from the explosion into the nose cone and then doesn't deploy. It just falls to the ground. So I would recommend, if you get the same rock, that you pack the nose cone with a little bit of wadding also, just to kind of keep it from getting the parachute stuck. Now that you have that all done, the parachute has wires, and this rubber shock cord is what it's called, allows the rocket to bounce on the parachute and not snap the parachute apart when it deploys. So you fold the parachute up carefully, and there's all sorts of methods, and you can look online to see what the best way to do it is. You got to get the rubber cord in here first, get it started at least, and then you take the parachute and poke that in there, and you just kind of pack it in there the best you can, and then you start packing in the cord and the rope, and it fits in there. You got to poke it down a little bit, but you want to make sure that you don't poke it too tight, and that you also have the ability for it to deploy. Another thing that's key is this nose cone has to come off easily, and there's a whole thing in the kit when you buy the rocket that describes how to keep this loose, and normally the default is fine, so I wouldn't worry about that too much, but you want it to be able to shoot off when that thing explodes in there. So now that you have the rocket all finished, it's a good idea to weigh the rocket. Let's get this out of the way. And so basically, I have a scale here that's in grams, but it goes in groups of 5, so it's not terribly accurate. I would suggest getting a scale now, and don't spend too much on the scale, that goes in single gram increments, not 5 gram increments, but it's too late now, so I'm using this. So this comes up to be 65 grams with the engine, the fuel, and the actual rocket. And so at 65 grams, there's a chart that actually shows that this engine can carry 71 grams. And so what's interesting about that is that only gives us, see, it's even changing because it's not very accurate, but it's basically 65. That only gives us like 6-7 grams to play with to strap onto the rocket. Well, I would like to add this data logger, which is 20 grams plus a battery, which brings it up to 30. And so now 30 plus the 65 makes it 95 grams. This rocket can't pick that up. So I'm not sure what will happen. I don't know if it will basically sit on the rocket launch pad and just sit there and burn and do nothing, or if it'll just not go as high, or if it'll go out of control. So I'm not sure really if this rocket engine, it's a C6 engine, is really what we want to use. I've ordered some B size engines, which will allow me to lift 113 grams. So the 65 here and the 30 here brings us up to 95, which is under the 113 grams. So with the new engines, I will be able to strap this onto the rocket and fire it off. Now this is the data logger right here and the supporting battery to run it. There's also another thing I would also like to experiment with, which is this little camera. This is basically a key fob camera. The camera's there, there's a microphone, there's an SD card here, and there's a charging port here to charge a little battery that lasts about 30 minutes. And basically this weighs 10 grams. So the 65 plus the 10, these two combined brings us up to 75, which is just a little bit over the 71 grams. So I think with this engine, I believe that this camera will work. So let's get this out of here. And so I think with these engines, this will work, but in order to use the data logger, I'm going to need a bigger engine. So that's something to keep in mind when you fire off your rockets. And there is a chart that tells you what rocket engines will carry what cargo load. And so pay attention to that as you design your rocket and your module. I do have extra wires here. If I was clever, I would basically make a little mini circuit board that I would solder this and this and this module together, so I have one solid unit that can strap to here. I don't have that, so it's not going to work. For me, I'm just going to do it this way. And I have some leads here that will allow me to attach the battery. In addition, I've connected wires here. I've also used some hot glue to glue the wires together and to the board, because when this thing fires off and lands in the sand, it's going to bang around, and I don't want the leads to come undone and I have to sit there and try to redesign this out in the field. So that's also important. So I'm just using a standard SD 4 gigabit SD card and just a standard SD module. I think they probably have smaller modules now. This is 3.3, this is 5 volts. I tried it with 3.3, and what happens is if the battery doesn't supply enough current, enough voltage to power all this, you can wind up losing your SD card. It kind of unformats it and makes it unstable. So I suggest using 5 volts for the SD card and 3.3 volts for the altimeter module. And it's called a Micro Mini Arduino Leonardo, and it already comes preloaded with the bootloader for the IDE for Leonardo, and it has a little plug here, which is a standard micro SD card. Micro USB connection. And something that was interesting with this is I have about 4 of these cables. None of them worked except for this one, and I think. And I knew it wasn't working because these little LEDs never lit up when I tried to load my sketch onto this board. You need a higher end micro SD cable so that it doesn't have it's just not a power cable, it actually has a data cable incorporated. So if you're having problems connecting to this, it may not be your connection, it may actually just be your cable. And I wanted to bring that point up so that you don't get disillusioned and give up. Try a good cable. It's definitely what you need. That being said, this configuration is set up in such a way that I'm using SPI interface or communication with the SD card reader and writer, and with the altitude module, I'm using I2C. And you have to configure this micro Leonardo board in such a way so that you can incorporate both forms of communication. There is a MISO connection, and you connect that straight forward, and you connect the 5-volt to this, and then you use the SB2, the I2C communication with A4 and A5 pins, analog 4 and analog 5, on the micro Leonardo Arduino module. And ironically, the A4, because that's what the libraries use for I2C. And so the SPI library connects to this, no problem, that works. But the I2C, the A4 and A5 chips are not, or ports or pins are not labeled. And so what I had to do is I had to look here for A8 and count backwards, and that worked. It was kind of a guess, but it worked. It went from 8, 7, 6, 5, and 4, and sure enough, that worked fine, even though they're not labeled on here. And getting information for this module is near impossible. You've got to kind of guess. For instance, the power pads for the battery, there's no manual that I can really find very easily or data sheet that makes much sense. So I just guessed, and sure enough, there's a plus and a minus, and then there's an N and a P for negative and positive. Well, I just connected to the plus and the minus for the battery, and that works fine. So there was a lot of guesswork. You don't use all the pins on the altimeter, the altitude meter. You only use the first 4, which is voltage, ground, SCL, and SDA. The other 2 I don't even use. And so that worked fine for me. What else did I want to mention here with this is, so they all connect together. The altimeter here meter uses pressure in its calculation, and there's 3 or 4 different libraries. You can use an Adafruit library. You can use a SandSmart library, but neither one of those really worked well for me. The one that I found that worked was the SEED, S-E-E-E-D library, and it was small. It didn't have a lot of extra data or calculating stuff, so I didn't worry about the other 2. I just used SEED, and that worked for me, because all I want is the pressure, because pressure is part of the calculation for the altitude. And the pressure changes depending on the weather. And that's another issue that you need to kind of take into consideration as you do the calculation for your altitude. And I'll show you that in the code and stuff. But sometimes it shows I'm at the altitude here. I'm at, 30 feet, and sometimes I'm at a negative 250. Well, it depends on if it's raining outside or not, or if the pressure's different, and so you have to take that into kind of consideration as you use this. There's going to be a little bit of fudge factor you're going to have to kind of take into consideration. I also use the mils for calculating the time that this has actually been running, to show as it takes off how much time has elapsed, and then I will graph the time versus the altitude, and all that has to be calculated in and taken into consideration. What else? One thing I also wanted to mention was I soldered these pins in a bad way, upside down. The board here doesn't have any lettering or any description of the pins, and it does over here. And I thought it would be clever to put the pins where you could see the lettering. No, you should do it the opposite way, so that the lettering, and that's what I did over here, so that the lettering of the board is on the opposite side of the pins. Makes it a lot easier to do. If I had to do it again, I would have the pins coming upward on the opposite side of where it's labeled, because it's really tough. Once you start getting these header pins plugged in, you can't read everything. And in fact, this board on this side covers up the ground pin, which it took me forever to find, and I would have done it differently. So I may buy another one of these and solder it correctly, or maybe even try to unsolder these and move them to the other side of the board. that will save you a little bit of headache also. What else can I tell you about this? You do wind up using all the pins for the SD card. It's a little bit big, but it works out. And what I'm going to do is I'm going to take some plastic wrap, like saran wrap, and I'm going to wrap this whole thing, and then I'm going to tape it, literally just tape it to the rocket like this, and then fire the whole thing up. I'm going to fire it off. I'm going to have another piece here for the battery, maybe on the opposite side, and just tape it like this, and then have these pins connect to here. Let's say this is connected. We'll just connect it like that, and I'll just tape the whole thing together, and I'm going to fire it off just like this. It'll all be shrink wrapped and held together, but basically that's how I'm going to fire it off, and that'll be that module. Now for the camera, I'm going to do something a little bit different. I'm going to I'm not going to shrink wrap it because the camera actually has its own case. And this is the lens right here. I am going to tape the camera onto the rocket right about here and like this. Because, and actually it won't be like that. It'll be on the opposite side of this bar. That's where the rod goes through. It'll be just like that, and maybe a little bit more over so that it gets through here, maybe like that. There we go. So that's better. And I'll put it on the rod. It'll take off and it'll film. Something to keep in mind is that I looked at. There's a data sheet that I will show you on where do you put the camera. Now this is kind of large and you don't really have much of a choice. It's gonna go wherever it fits and however it fits best, and that's gonna be that. I don't have much choice with this. And there's actually two parts, a battery and this. But this is relatively small, and so where do you put it? You put it here, here, down here. I initially thought that it would be a good idea to tape it here because that would seem to make it most stable. Well, it turns out that's not true. The most stable place to put the camera is at the top, up here. And why is that? Well, it turns out that there's two things you need to keep in mind. There's something called center point, which is the center of the rocket. So the rocket is 12 inches tall. The center is at 6. Let's say the center is right here. Then there's also something called center of gravity. Now the center of gravity is where the rocket is balanced, not the center of the rocket. So you see, now my finger's a little bit large here, but you see that's the center of gravity. That's where half the rocket and the other half of the rocket with the engine is balanced. The center of the middle of the rocket is here, and it would fall over. Well, you want the camera as far forward of center of gravity as possible, because what that does is the fins act like a leverage. And so if you're here and this is out here, the fins can stabilize as it cuts through the air, the rocket imbalance of the weight of the camera. If it's down here, it can't. It doesn't have any leverage. So that's what's key is the leverage of the fins. The further out, the more leverage the fins have, because it's like a rod. It's like a leverage. And so that was counterintuitive. I really thought this would be the best spot. Well, this thing will fly out. It'll go crazy. You put it up here, it'll go straight up, and you'll get a perfect image. So that was something that was counterintuitive. And I think with the data logger, I think since it's so long and the weight is balanced throughout the thing, that I can probably mount it just about anywhere along the side of the rocket, and it'll be just fine. And I'll do the same with the battery. I probably will mount the battery more towards the top so the fins can come into play and correct it a little bit more. So that's basically the hardware makeup of the rocket and the data logger and the battery and the camera. Now let me mention some other things that I want to let you know about the hardware. You know, I told you about the cable. If you are trying to figure out what battery to use, if you're not careful and you have too little power to the data logger, you can damage the SD card, and because it doesn't have enough voltage, whatever, or current to write the file, and then it winds up destroying. You get some weird file name, and it just destroys the directory, and then the card doesn't work. There's another thing is I told you about the rod. I told you about writing the information on the rocket. Basically, I told you about this camera. It's an 808 camera, a keychain video camera. They have different modules. This is a number 16. They make a number 26 that has a wider angle camera and some sort of video out. This is the cheapest one for 10 bucks. I suggest using that, and it works great. It also has a microphone, so it does record what you say. Just keep that in mind. I got that at Amazon. I was going to use regular batteries, but I really want to use regular batteries like these in a pack like this. But this is way too heavy. It'll never take off with all this. So you have to figure out some sort of LiPo battery to mount with this if you want to fire the thing off. There's another thing. I mentioned the cable being an issue. Lastly, I want to mention when you fire off the rocket, it's got to be a clear day, because some of these rocket engines go really high. They go over 1,000 feet, and no wind. If you get some sort of wind, this thing can blow all over it. Once the parachute is deployed, once the parachute in here pops out, the wind could take it miles. So you want to make sure there's very little wind. One thing that we are going to also include, which you don't see here, is and I'm not sure how loud it's going to be, is going to be a buzzer. I'm going to strap a buzzer onto it so it makes a noise and it makes a continual noise as it's fired, so that when it lands out in the distance, we can hear where it is and hopefully find it. They also make a GPS module that's about 10 bucks, maybe $15 that I found. You need a little SIM card from a phone and an SD card, and you put it in there, and you can actually text to the GPS, and it will tell you within about 500 yards, I think it is, or maybe 500 feet, where the rocket is on Google Map. So that would be kind of cool to do. It's a little bit more than I want to spend, and we'll see if we actually do that. You have to have internet connection and that sort of thing. But that might be a good little project to also include at a later date. Once I get more familiar with how this all responds, I'm not sure when I fire this off if this thing's just going to go haywire. I don't know. So we'll find out, and we'll see. So that's basically it. And I think that this is a good rocket to start out with. It takes a wide variety of rocket engines, so you can do different projects and different degrees of height and that sort of thing. This is the camera I'm going to use with the model rocket. It's an 808 car key micro camera keychain. It's basically a little recorder that allows you to record onto an SD card. And it's very popular with the model rocket folks that use model rockets, and they attach these to their rocket basically just with duct tape, was what I've seen in the past. It's inexpensive. You can get it on Amazon for about 10 bucks. This one is the smaller. There's 2 or 3 versions that I know of. This is a number 16. I think there's a number 26 that has a wider angle lens and FPV output and stuff. It's quite robust. But I didn't need all that. That was like 30 bucks. This is under 10, I believe. So I think with shipping everything, it's about 10. So let me show you what it looks like. It comes in this box, and I've already removed the key ring because I don't want to send that up. That adds extra weight. Here's the camera itself, and there's instructions down there, and that's all that comes in the box. The camera itself is really small. There's the lens right there. You may or may not be able to see that. These 2 buttons up here are faux. They don't do anything. There's only 2 buttons. There's a power button here, and then a take a picture button or take a video button. And that's it. You charge the battery here using this micro USB port. This is reset. You have to install your own SD card. That might be kind of hard to see, but there is an SD card slot right there. And there is a little microphone right here, so it does video and microphone. So it's really quite nice, considering what's all impacted in this, packed into this little container. Again, I don't need a whole lot of features. What I do like about it is sort of aerodynamic. Not that that makes much difference, because I'm just going to take this right to the rocket. Here's the rocket here. And what I've read is this is about where you want to put the camera. It was up here near the top. But let's weigh this first, and you'll see that it weighs 10 grams, which is extremely light. So I'm hoping that this rocket will be able to pick up at least 10 grams. But back to my point, why you want to have the camera mounted here versus in the center here, or intuitively you want to put it down here by the fins. What I've heard is when you have a rocket and you attach something to it, basically the fins act as leverage. There's a center point, and then there's the center of gravity. The center point is the actual balance of the rocket. So if you hold the rocket here, and I don't have a motor in it or engine in it, but that's basically about the center point. But the center of gravity, I mean that's the center of gravity right here. The center point of the rocket is about here, so it's about 1 inch or 2 inches off from the top of the rocket down to the bottom. The center is about here. Well, when you have a camera too close to the center point, it gets all unbalanced. If you have the camera down here by the fins where you'd think it would be, the fins kind of don't take into consideration leverage. So what you want to do is you want to have the camera further than the center of gravity. And the fins will have more leverage because, ideally you like to put it way out here, because then the more leverage you have with the fins, with the wind, as it thrusts into the atmosphere, the camera weighs less. But if you have it close to the center point or to the fins, you remove that leverage capability. So that was very counterintuitive to mount the camera near the top versus down by the fins. So we're going to do a test and see how that works. But other than that, very happy with the camera size and the weight, and we'll see how it works. Well, I wanted to show you some of the websites that I used to build and design this project. First and foremost is this module right here. It's the AT Mega 32U4 BS P Micro Pro Micro Leonardo Arduino compatible development board. And it's really a powerful little board for only $7.50. It's very lightweight and very small, and it has quite a few pinouts. I'm kind of going through them here. If you look here in the back, you'll see that it has master out, master in, select clock, or system clock, and a TX and an RX, and all sorts of, here's ground, 3.3 volts, here's 5 volt, and it has 16 digital pins, and it actually has about, it looks like 8, maybe 10 analog pins, analog 11, analog 10. So it has quite a few analog pins. It also has a plus and a minus here so that you can solder your own power supply, which is what I did. I tried to find out what N and P were, like negative and positive. The company never got back to me on that, but so I went ahead and just soldered it anyway, and that's right where the battery goes. So that worked out great too. So this is a great pin, a great module. It really made this project feasible. You have a mini USB connector here, and it's imperative that you get a good data cable USB cable, not just a power USB, but actually a data USB. And I have 5 of these cables, and it doesn't come with a cable, but I have 5 cables, and 4 of them did not work, and I was starting to think my module was bad until I finally found one cable that worked. And sure enough, this thing worked like a gem. The only negative thing that you got to keep in mind is it only has 28K of storage of onboard memory, so you can't write really big programs or include large libraries. But it does support I2C and SPI, and because of that, I was able to do this project. So I wanted to kind of show you where I got this. This is at banggood.com right up here. And let's move on to the next thing I want to show you. This is just a standard SD micro TF card. You put the SD card in here, and you connect these pins here. Let's see if it has a pin out. It doesn't have a pin out, but basically it has MOSI and MISO and clock and a chip select. So you use for the SD card here, you would use SPI interface, and it's inexpensive. And I had one actually already lying around, so I went ahead and used it, and it worked great. The next chip is this chip. This I actually got from AliExpress. It was $2.50, and I'm sorry it's in Spanish. I can't seem to get it to show in English. But AliExpress, this is the BME 280. This is a dash 5V. I actually got a dash 3.3 for 3.3 volts. So this worked on 5 volts, and the altimeter, altimeter / pressure humidity module here worked on 3.3 volts, and it worked great. Very, very small. So the 3 components are this module here, which is the micro Leonardo, the SD card module, and the altimeter, and all of that, not including the wires to hook it all up, came in at about 20 grams, which is important because you really want to keep the weight down. If I had to do this again, I probably would make my own circuit board and solder these 3 components together onto a little circuit board and then wrap the whole circuit board and mount it to the rocket. But that's a little bit more than what I want to do for this project, but maybe some of you out there want to do that. So I did look at this module. It was $19 at Adafruit, and I didn't want to spend that much. There was another one here that was $9.95, Arduino Pro Mini, which probably would be a good board to use. Also, it had quite a few more pins than what I needed, and it was much larger. So I went for the smaller package here. It was lighter weight, and I didn't need all the extra pins. Here we go. I would encourage you to buy this, though. This is actually not a bad price, and it has a lot of function. One nice thing is it does have a reset button. That would have been kind of nice to have, but I didn't really need it. Next, you need, I'm sorry, here's another barometric pressure sensor. It's got a little bit more stuff going on. I didn't choose to get this one, but I did use the library from here. I used the seed library, and I'm not sure if I have that information up here along the top, but seed has a library for this, and I downloaded that library. Trying to see if it shows it here. Down here it talks about getting the cable. Anyway, in here it has the library that you can download from GitHub. And in fact, I don't know if I have it. Here's the GitHub. Here's the seed library, and you just download this here and install it. You get the Grove BME 280, and it's a very bare bones basic library. It was all I needed. I didn't need a bunch of other fancy features. I didn't truthfully have the room on the mini micro Leonardo to store it, so I didn't really want it. So this worked for me. SparkFun has a board also, and they also have their own library. I did not get this one. This was $19, too much. This was a video that shows how to program this module on YouTube. It was really kind of one of the things that kind of got me going, thinking, how do I use this with the rocket, which I'll show you here in a second. This is a very good video called BMP280 Pressure Sensor Module to Arduino tutorial. You can search on that, and it's Adian. I guess he's the one that narrates it, and it's his thing. So it actually worked out quite well. That helped me out a lot. Next, I needed a camera, and I researched it on the websites of model rocket groups, and this is the camera of choice. It's the 808 keychain camera. Don't use it as a keychain. It breaks instantly, but it does have a microphone. It weighs only 20 grams, and I think this one's only $12, so not very expensive at all. It has an SD card that you can store video and audio on, and it's in color. Works great. Take pictures if you want, but I just use it for the camera. Let's see. Let me go back up here to the GitHub. Here's the camera. If you want to get some software and edit the camera, it's called the number 16 camera, and you download your language here for the software, and you can flash the camera to have different higher resolution, no audio. You can change the way things function with the buttons. I didn't do any of that because I just want the camera to work so I can fire it off using an Estes rocket. Now, I didn't use this one. This is their Estes website, and what's nice about Estes is they have this education tab and a rockets tab if you want to buy the rockets. But the education tab has all sorts of folders and PDF documents and all sorts of things that are really helpful. And I will go into those later, but really, really helpful. I thought it was just amazing, all the technical data you can find out. This was a forum that talks about anything related to rocketry. That's what it's called, the Rocketry Forum. I actually found out where to put a camera. It's technical. There's a lot of information here, but a lot of your questions can be answered in this forum. I highly recommend it. Moving on, this was the rocket kit I bought. It was I want to say, I don't know why the prices aren't on here, but it was about $25. And it includes a rocket control with batteries that ignites it, remote igniter, a launch pad, a rocket that you assemble, and a parachute. And it's a great way to start out. This is a great rocket to use because it has all sorts of different rocket engines that you can use. And I found that it's nice to have options with the different rocket engines, which I'll show you, because different rocket engines have different cargo lift capabilities in grams, so it's really important. But this is a great one to start out with. You don't have to worry about the fins. It has plastic cone. Really easy to assemble. A lot of fun. Moving on, you buy your rocket engines here. Here's a rocket engine. Buy another rocket if you lose it. I lost one. But you get all these different rocket packs, and they vary in different prices. Something to keep in mind when you buy a rocket pack, not only do you get the rockets, but up here you can hardly see it. You get a little bit of wadding paper, which you're going to need. You get some igniters. You get 3 igniters, I believe, 3 or 4 igniters, which you're going to need, and some little plastic plugs. Now, you can go out and buy extra plugs and that sort of thing. This is an extra pack of wadding here. This is an extra pack of plastic plugs, some extra igniter wires. They all cost a couple bucks. If you're nervous about losing it or something, buy some of the extra equipment. It's nice to have it when you're on site because you don't want to run out and then have to leave because you're missing a plug or some igniters. So some other things I was thinking about also firing off with this rocket is this little GPS module. It says €12. I don't know what it is in dollars. Maybe it'll tell me up here. Convert to dollars. So there we go there. I don't know if that works or not, but it's $14. And it's kind of cool. There's a little software package that goes with it. The thing is, you need to put in a SIM card here for a phone, and then also an SD card. And I don't want to go out and buy a SIM card right now. What you wind up doing is you wind up texting using an app that you download to the GPS to configure it and turn it on and search for it. So. But it doesn't, it seems like a cool little thing. It'd be fun to use to find rockets. We'll see. I might do that for a different project. Here's a little buzzer that I did buy, and I'm waiting for it to show up. I was thinking of, it's about 90 dB. They call it a panic buzzer. And basically what I'm going to do is you pull out this pin down here and tape this whole thing to the rocket, and it just makes a continual noise, and you fire it up in the air, and wherever it lands, you can go find it. Since I lost one rocket, I thought for $2 this would be a good thing to try out also. Here's how to update the keychain phone. This is another video. It's part of, goes along, I think, with this software. So I just did not choose to update the phone, but this is another good website, YouTube video to watch. This is a guy that actually has this is his web page, but he has a bunch of model rocketry that is very cool. He's really into it, but he explains it really well. His videos aren't too long, and it's kind of cool to watch him launch some of these larger rockets. He's very knowledgeable, and I would encourage you to look at the first couple rocket videos. He kind of is trying to duplicate SpaceX and have the rocket land back in front of him. And he makes some components that does a rocket thrusting engine, a thrust vector, so that the rocket engine actually pivots so the rocket stays upright. And he's made his own little onboard computer and altitude data logger like I have, but his is probably much more sophisticated. But anyway, it's interesting to see what he does, and if you're interested in rockets or want to get into computers and rockets, this is a way to go. This is a sample of one of his videos. He actually winds up firing off this large rocket. He's got a camera. He gets really into it, and he does good work. The last thing here is, as far as websites, is Python. I used Python on the back end to take the data from the data card that I logged from the rocket launch and to actually plot it. And in order to plot it, you need some libraries, and this is called PyPy, Python Package Index. This is where you get all the libraries. You just type in the library you need, like NumPy here, or MATLib. That's all one word right here. Anyway, you need all that, and you'll see how to download it. I show how to download these in another one of my videos that includes Python and the Amazon and the Arduino. And so very, very powerful stuff. I'm going to do more of my videos using Python and the Arduino, communicating, doing some cool things. I wanted to go over some of the Estes publications that Estes offers on model rockets. There's a lot of information out there on rocketry. You can imagine that it's a pretty intense topic, but if you're more interested, I found a lot of it very interesting. Not a lot I could use. Some I definitely could use. One of the best resources is the Estes site. and they have something called education, and this has a web page, and underneath over here on the left, when you go to the education tab, it'll say publications, and then you'll get all of these educator publications, and they have all sorts of different types of PDF files you can download. Rocketry 101, model rocketry, technical models, elementary math and model rocketry flight, all sorts of things that you could find interesting. You see it goes on and on and on. They have their basically technical report on boost gliders and launch systems. I highly recommend checking out this website and looking at some of these publications. There are a couple publications that you should download for sure and take a look at. One of them is the Estes engine chart, and I'll show you those now. Let me start with this one. Here's the Estes model rocket engines. This is one of their publications. In fact, I have 4 of them across the top up here that we're going to look at. But I encourage you to look at all of them if you have time. They're a lot of fun. This is the breakdown of an Estes engine, how it works. There's a clay nozzle at this end, and then there's a clay retainer cap at this end that blows off and lets the parachute deploy. And there's all sorts of different chemicals inside. One is the liftoff propellant. There's a delay that makes tracking smoke, and then the ejection charge that blows it off. And you can see down here how it all works, and it's explained over here very nicely. What is key is this information at the bottom. Right here. The color coding is important, and the color coding refers to the color of the lettering on the Estes rocket. Green and purple are basically what I've been using, and you can see here that it's a alphanumeric digit. This is a B6-4. The B stands for total impulse, and explains how the lettering doubles in size with each lettering as you continue to go through the alphabet, A through E or F. And then so the average thrust is the next letter, and then the dash is the time delay. And so you can read this and find out actually how these rocket engines are working. And depending on what you want to do with your rocket, what devices or modules you want to lift into the air and, say, take data or video or whatever, this information becomes very pertinent. Now, there's another chart that you're definitely going to need to download. It's called the Estes engine chart. And basically, it goes through each engine type. The lettering I was telling you about here, here's the B64. And what's important are max lift weight in grams. Now, you can do it in ounces, but grams is more accurate and easier to calculate, I think. Now, a B64 has 113 grams of liftoff capability. Well, that's interesting because if you go past the thrust and the duration of the thrust, the initial weight of a B64 is 20 grams. And that is the weight of the rocket engine. And the propellant weighs 6.24 grams. Well, if you have a rocket that weighs 35 grams and the rocket engine weighs 20, you're now at 55 grams. You have quite a bit of room here, almost a little over 60 grams, almost 60 grams to lift. And if your data logging module is only 35 grams and your camera is only 20, well, you should be able to lift both of those. And that's why this chart is so good, because you can figure out what engines you want to buy. Like, for instance, let's say you want to go really high. A C67 will go really high, maybe 1,000, 1,200 feet, but it only can carry 71 grams. Well, if the rocket weighs 35 and the fuel weighs now almost 27, because you have to carry more fuel to go higher, you're getting pretty close to that limit of what you can carry. So this is a very interesting chart, and I highly recommend you downloading it and analyzing it. What's interesting is the propellant category over here too is here, this engine, let's just take the first one here, can lift 28 grams. Its initial weight is 5.6, but it loses as it burns almost 1 gram. So at the end, this will weigh almost 4.8 grams at the end. So actually the weight changes as the engine burns the fuel. And that also will affect the center of gravity, because as the fuel burns, the center of gravity will move. And some of those other technical documents I showed you on the Estes site will explain that. So I highly recommend that. So here's one of those PDF files I thought was interesting. It's one example of a whole list I showed you. Rocketry 101, Estes model, rocket basics. This I downloaded because I find it kind of interesting for our group. There's a group of us that are actually going to fire off this rocket. This explains model rocket flight profile, how it takes off, it ejects, it recovery, and then it comes to the ground. You can read it and see how it all works out. But it's very interesting, the whole series of phases it goes through. Here's components of a typical model rocket, the rocket that I bought and I suggest you buying. Here's all the terminology: the launch lug, tape rings, shroud lines, nose cone, shock cord mount, engine hook. I mean, they all get into rocket technology, which is kind of fun to know and to talk about. Lastly, here's the launch site layout. We are going to do this. We actually lost one of our rockets on a windy, foggy day. It's got to be clear and calm, or you will lose some of these high-flying rockets, no doubt. You need over here a recovery team. You need trackers on the side, a good launch control, they say officer, but a good clean launch control site so that you can at least launch it when everyone's away. Here, number 5 is a preparation table. That would be nice to have, but you could use your launch table as the same thing. So this little layout is nice to have to kind of show people what to do if you have a group of people working with you. And this is critical because we're going to be launching devices up in the air like the altitude data logger that I want to recover. I would need that back. And so here they talk about recommended launch area. The first engine I tried was an A-type, and we could easily see the 100-foot square radius or circumference, around the square easily. But when we fired off the C, we're now talking 400 feet, and the C engine I think I fired went 1,200 feet in the air. We lost it. And 400 feet is larger than a football field length and width. And you're talking a huge area. So it's important to lay out your recovery team and ground crew very carefully in order to get that rocket back. So when you start using these higher altitude engines, which you may want to do, take this into consideration. Print this out and take a look at what you need to do. And then here it talks about the rocket engines again, and which is you have earlier. Here it talks about how to select an engine. You can buy extra recovery wadding. That's that paper that doesn't really burn so well, so that when this thing blows off, it doesn't burn up your parachute. Here's the igniters, and you can buy all this extra little plastic plugs. Buy bulk packs if you want. And here's the engine sequence of how to rocket pre-flight preparation. Tells you how to do it. Again, a picture of the plug, the igniter, the engine, the rocket, the cone. And there's all sorts of methods for folding the parachutes. Normally, your rocket is so light, if it falls out of the sky at a low altitude, it won't get damaged. Ours didn't get damaged when it landed in sand. But if you're landing on ground and you got balsa wood fins, they break. You can't fly anymore. So this is all important. Here it goes through how to install it. Some pyrotechnic information about the igniter. More information about bending the pins. So I highly recommend Rocketry 101 pamphlet to download. Lastly, these are the instructions on how to build the Alpha 3 rocket. I recommend starting out with that rocket. It's a great rocket. You can go through this and see what tools you need, the glue, maybe some tape. It's real simple, straightforward. and it gives you kind of a heads up on, it takes a couple days. You got to use the glue. It has to dry. You need a knife. You need some glue, maybe a ruler, some scissors. Anyway, this is a great rocket to start with. I highly recommend downloading some of these pamphlets and taking a look at and reading some of the pamphlets. This is the Arduino sketch that I used to generate the data logging altimeter module for the rocket. There are a couple things you need to get started. You need to have the SD card writing library. You need the wire library for the communication for the altimeter. And then you need the SEED BME 280 altitude and pressure routine library for the pressure and altimeter calculations. I put in Pragma once here because then that stops opening multiple .h files. So if you get, I think I was getting a multiple SD.h, and so I put that in and that got rid of it. So if we read the header block here, the comments, it says this project uses both SPI and I2C communication to log the altitude and timestamp to an SD card. The SD card data will be uploaded to a laptop for graphing using Python 3.7. A limitation of the mini micro Leonardo is that it's 28,672 memory byte size. That means if your program and you load too many libraries, you will run out of memory and it won't save it. And you got to also incorporate some memory for variables. At the end of each launch, when the power is removed, a data XX, and the X's are numbers from 1 to 99, .txt file will be created with a 0 byte size. So as it's logging, it will create new files, up to 99 files on the SD card. But in the middle of that, if you decide to disconnect the power because you're done with the launch, you don't want it to continue to calculate the altitude if you're walking around with the rocket and putting in a parachute and putting in a new rocket engine, the last file will be 0 and there won't be any data in it. It'll be kind of a funky file. So you don't want to process that file, and I'll show you that later. I was not able to get the Adafruit or the Sane Smart altitude libraries to compile with my software, so I went with SEED and that worked fine. The altitude value is based on the calculated pressure reading. The pressure reading is based on the weather conditions in the environment. So if it's raining where you live, or it's windy, it's hot, it's cold, the pressure will change, the altitude would change, and you'll get some odd readings. So it is not uncommon to have the altitude read 30 meters one day and minus 250 meters the next. So just keep that in mind. You have to create what I call here an offset must be used to calibrate the altitude to 0 each time the sketch is run. And I kind of did that. I did the best I could, so you might want to improve on it. A variable could be used to manually enter a current day's biometric pressure data from a weather site on the web. Yesterday I checked, our barometric pressure was 30.08. You could, if you wanted to spend time on getting a really precise altitude, you could put that data in for that day and run it, and you'd get a much more precise altitude. But it's not necessary for me. This would provide the necessary correction. Some things I want to mention also, our SD card runs on 5 volts and communicates over pins. The MOSI is pin D16. The MOSI pin, it says pin S0, but that's something else. The MOSI pin is D14. On the SD card, the clock is D15. This is on the Micro Mini Leonardo board. And then the chip select is D13. And I also specified chip 13 down here. The altitude module communicates over I2C communication on 3.3 volts. So one is 5 volts, one's 3.3, one's SPI. Yeah, this is actually SPI on SPI 5 volt communication. And this is I2C 3.3 volts. It uses D2 and D3 for A4 and A5 respectively, even though the module, the mini micro Leonardo, does not label it 4 and 5. It is 4 and 5. I basically counted back from A8 on the little module which is labeled. Respectively, for the altimeter to work, I2C uses A4 and A5 pins in the seed library, so you have to get to those. So some variables I created here. My files is to create a data file name to access the SD card. Here's the chip select pin. Here's the start time. I save the start time whenever the power is plugged in, so that we have the correct amount of time that has transpired for the altitude to be calculated. Here we define a base file name called data, so all the data files will start with the word data. This is a base name size. This uint8_t is really means byte. So this is a constant byte size of file name -1. So we have the file name -1 here. So it goes from 0 to 3. It kind of creates, I guess, like an array. Here we have the file name is the file base name plus 00.txt. This portion is so the very first file is going to be data 00.txt. We create a float variable called pressure and a float variable called alt weather offset, because this is the correction for the weather when calculating pressure and altitude, and I'll show you that down below. Let's see. Then we create a BME 280 object for the altitude, and then we start the setup. And here in the setup, we start the serial begin. Even though I had some problems printing to the serial, I never got this device error message because the serial print never worked for this serial monitor over here. It never seemed to work. I think that has something to do with either the serial communication with the mini micro Leonardo module. Sometimes it would work. If I did something really simple like print hello world, it worked, but here it didn't. So I never figured that out. I didn't really need it. Basically what would happen is the card would just hold and nothing would happen, and the SD card would be empty if here we configure the SD card, and if there's a problem, it just never records. Or if there's a problem with the BME 280 altitude module, it just didn't record anything. It just stopped. So I knew whenever the SD card was blank, something went wrong. So that's kind of how I used it. Continuing on, we create our first file name, and I'll show you the function down below. Pressure, we get the pressure using this command here, calculate the atmospheric pressure data using the BME. Like I said, it could be negative, so don't be too freaked out. Here, if it is negative, I subtract everything from 0. This is the offset I was talking about, and basically this will start everything off at 0. So if this pressure is 30, it will be 0 minus 30. The offset will be a minus 30. So 30 and minus 30 give you a 0. So this helps you zero out regardless of what the weather pressure is. If you get a pressure of minus 250, 0 minus 250 minus a negative 250 is a positive 250. So down below I add these together and I get 0. So I'm always having the weather offset. I always have the barometric pressure 0. No matter what it actually is. So moving on, there's a delay to allow the module to have some time to process this. And then I print this, pressure information, or this altitude information, where you calculate the altitude, in the very first data 00 file, right here, data 00. And then after that, I print a header, and I call that file, the data00.txt file, a header file. And I say, create a header file with the message new launch. It delineates each new launch due to the less than 15K file size. So as you're looking at the directory, and I probably should show you that directory now. Here's the directory that it creates. Here are the file names. Here are the sizes, and so you can see the first file here has the those two entries, the pressure and new launch message, and it's 1K in size. Now your data files range from 14 to 16K in size, and then this one is 0 because this is where I pulled the power out, and so it never got written, and so it has a 0 size. Even though the file name got created, there's nothing written to the file because it was never closed. So here we print it. We print this new message log. We close it. We start our calculations for our stop clock for the time. Here's our loop. And our loop, we create a new file, which will be data 01.tx, and this will actually have data in it. And basically, when the data is written to the file, the data is written in a single line format with a float altitude data and delineated by a comma, and then float timestamp data. And I think I'll show you that. Here it is here. This is data 11, but it's just a sample. The altitude is 1.73 meters, and the timestamp is 26,978 milliseconds. Now, of course, when you graph it, you may want to convert this to seconds or minutes or whatever you want. And then this too, instead of having it meters, you might want to have it equivalent to inches or feet. And 1.73 is clearly it's a little over almost 5 feet or 4 feet because I have it up on a high table. Anyway, so that's why this is how the data comes across. And you can see just sitting on the table, it bounces around quite a bit. So when you go to plot this, you're going to have to do some form of smoothing, line smoothing, or else you're going to get really jagged lines, and I'll show you that later when we discuss the Python code. So coming back here, we create the file. We write the data. Here we go from 1 to 1,000. So I actually write in each data file 1,000 points, and it picks. It just fills those files up really quick. And here I calculate the pressure, and then I print to the file. I save the information in the data file at this alt weather offset plus the pressure. So I'm kind of offsetting the pressure here in order to get the pressure, and then I'm multiplying that by 3. And I'm not sure. This is actually, this is going to calculate the altitude here. So here it takes the offset of the pressure and we add it to the altitude. And I'm not sure. See, here we multiply that by 3, and then we put a comma. And then here we put the start time. We find out what the current time is, and we subtract the starting time. We get the difference. Then there's a little delay to write that, and then we close the file and we give it a few seconds to close, and that's where we start writing the data in the file. And this offset is basically part of right here taking care of the offset is the calc of the altitude pressure. So this will allow you to kind of zero everything out. So you don't get a minus 250 feet or plus 30 feet just sitting on the ground. And that's important for the rocket because I don't want the rocket to start off at 100 feet if it only goes 400 feet. So it has to start out at 0. Now, next we come down to create a new data file name, and that's what this function does. While the SD card, and this is called whenever we want to create a new file to write to, after 1,000 entries have been made, we need another data file. And so if the SD card exists, and it isn't corrupted or it's inserted, we check the file name, and what we do is we check if the ones position of the file name has reached 9. It has to be less than 9. Otherwise, we will then bump up the tens position. Well, if it isn't 9, we increment the first zero, the 0 by 1, the base name size by 1, and then we check to see if the tens unit is not 9, and if it's necessary, we increase the name size, the ones position. We reset the ones position to 0. Like, for instance, if we count up, if it is 9, then we bump it to 0 and we increment the tens position so that it's now 10, and we start this whole process over until we reach 99. Once we get to 99, we can't create any more file names, and then our error message is displayed, and we've reached 99 file count maximum. You can make this bigger, but I thought 100 was plenty. 1,000 files on a SD card is going to be too hard to manage. Next, we open the file with the new file name that we created up here. And if the file exists, then we continue. Otherwise, if it doesn't exist, for some reason it didn't get created, then we say open failed. And that's the end of the created file name. And that's all we do. We just keep creating new files, filling them up, creating a new file, filling them up. And that's basically what happens each and every time. And you might be wondering, what about the start time being reset? Well, what happens is you only restart the start time when you're doing a new launch, and then you create a new header, and then you start this whole new this whole process over again. And it works very smoothly. So all in all, this I found that it works out quite well, and it's not a very big program. So that being said, let's go ahead and move on to the Python program. Now, the Python program will read this directory, all these files, starting at this one. It will ignore anything less than 15K in size. It'll only grab these larger ones. It'll ignore this. And normally this one is not created, and it's not supposed to be put in this directory. I have it here just so you can see where it was stored, but you would probably want to have this stored to your desktop, this test.png, and I'll show you what that is. You only want data files created in the Arduino Python communication folder. So you load these libraries. You have pathlib, which is for reading data files on the laptop. Here's import OS. I think it's part of the operating system. NumPy or NumPy is part of array handling. That's what its expertise is. And lastly, the one that does all the mathematical stuff, the matplotlib. We import that as PLT. It does all the plotting and graphing. It does the workhorse of the program. So, reading this in this comment, this program is the back-end plotting program to graph the data.txt files generated by the Arduino sketch, and I called it, for all things, final mini Leonardo rocket SD card write altimeter.ino file that were saved to an SD card. The data files are copied from the SD card to a processing directory on the desktop called Arduino Python Communication, and are used for processing. Due to the sporadic nature of the altitude module, the data jumps around quite frequently. So a function is used to smooth out the data by using a moving average here in this Python program. Data files are processed one by one until the last one is used up. A valid data file must be greater than 1,500 bytes. There's a commented line to save the graph to a .png file in the processing directory. That was that test.png. I comment that out. I don't usually generate that graph, but I wanted to show you what it looked like. Coding notes. The line ax.plot time array minus sample size plus 1, comma, alt average, comma, r minus. The time array has to be shortened by at least by 1 less than the sample size and from the end of the array, because as you take the mean, that file will shrink because you're actually taking the files, and your window size or your element size, if you are averaging 3 numbers together, those 3 will be compiled into 1. I'm doing a sample size of 1,000, and those 1,000 files are being sample sized down to 1. So I'm losing a lot of data. I think I have like 80,000 points, and that gets compacted down to 80 points. So you need to offset the time array, because the time array is still 80,000. So you have to subtract from the end that information. The time array has to be shortened by 1 less than the sample size and from the end of the array. As the moving average is calculated and stored in the new smaller alt average array, it cannot be plotted 1 for 1 using the larger array. So the time array has to be reduced in size, deleting element entries at the end. And I think my time array is not super accurate. I really need to go in and delete 1,000 and then leave one data point, delete 1,000, leave one data point, delete 1,000. I haven't done that, and I'm not so much concerned how long it takes stuff really to go. I'm more concerned how high is something really going. So we'll see how this works. It's kind of in the process, but that needs a little bit more work. Is the time stamping array needs to be adjusted a little bit, and I may work on that a little bit more. So here we have the moving average function that actually plots the graph. You pass it the altimeter array and then your window size, your sampling size. You want to take every 3 and do an average, or a mean, or do you want to take 1,000 and do a mean? I pass 1,000. These 2 commented lines are for older code that for older moving average I used. I thought this new one down here I have is much more accurate, and I liked it. You set this weights to repeat through the array, and then you set the SMAS moving average size. I forgot what the SMAS stands for. I should have probably changed that to a better name. And it returns the moving average value. Here you use NumPy, that's MP, convolve, and it takes the altimeter array, and it takes the weights that you calculated up here and only the ones that are valid, and then calculates it out and returns it in SMAS. Now we have and so that's the function, and that's what the function does, and we'll call that down here. Now getting back to our variables, we store the altimeter data in this array, and we store the timestamp in this array, and our data folder is this folder here, and that's where all the data files are stored. And in order to plot something, you have to store the data in arrays. So I'm going to plot the altimeter array against the time array. So this is going to be the Y, and this is going to be the X, and it'll plot it 1 for 1 in a graph. So now here we read files, and for the range goes from 0, because the first file in a directory is 0. It goes to the length of the file directory, the number of files in the directory, and it'll go, then it'll open the file, the first one in the folder, which is this folder here on my desktop, plus the file name with an index. 0 is the first file, and on and on. And so the list directory lists the files from 0 to length -1. That's why you use the X. So stat info is basically the file to open. It gathers all sorts of information, and then from there, at one time as a debug, I printed the file size in bytes, stat info.st_size. That gave me the bytes. I use that for debugging, but I don't need it now. Now I save the data to a txt file. If the stat information is less than 15, the altimeter array is blanked out, so is the time array. And if the stat info that I got earlier up here, if the file is greater than 1,500, then I know that it's a valid data file. And I say file to open is equal to this file with this index, which will be data file 01, because that's the first one that's greater than 1,500. And I open that file here, and I say while f, the data line, I read a line of code, I read a line data entry, I read one line of this information here. And the altimeter is equal to, the data array. We split the data line using this command. one portion and the other portion by a comma. So I say the altimeter is equal to the data array sub 0, which is the left side of the comma, and this timestamp is the right side of the data array, or sub 1, and that's on the right side over here, and then I put that accordingly into each array. Altimeter array is, I append the altimeter array using altimeter, which is this value here, and I keep adding it up every time we circle through until we've read the whole file, and I do the same thing with the timestamp. And that's how you fill up each array that you're going to plot down here in plot graph. So in plot graph, we say next file to open is equal to the folder, our data folder, and here is a listing of the file of the following file, and I say next stat info, which is really the next file, is this information next file to open, because if you have only one file to open for data, that's fine. But what happens if you have 8 or 9 or 10 files? Well, you have to append all of those files into one huge altimeter array, if that makes sense. So if you have 80,000 entries or 80,000 samples like I did, and you want to plot all 80,000 samples, you have to append them, but you have to read across multiple files like data01.txt, data02.txt. In fact, you can see here, I actually read 1, 2, 3, 4, 5, 6 files before I get to one that's invalid. So I have to append all of those files over and over and over, and that's what this next file allows me to do right here. It lets me look ahead to see if the next file is a valid data file or not. So moving on, I say here we have a file that is less, my sample size is 1,000, and we're plotting the file now, and the alt average is the moving average, and I pass it the two arrays, the altimeter array that now may be 80,000 elements, and a sample size, which is 1,000. So I'm going to take 1,000 elements, add them up, take the average, and that's going to be only one entry in the alt average array. And now this will plot the subplots for plotting, establish a plot, which will establish part of the figure to show on the screen. Here I give the time array, and I basically here I subtract out sample size plus 1 minus sample size plus 1, the extra timestamps. And this is really where the work needs to be done, where I deduct every thousand, I deduct a block, and then I leave a timestamp, and I delete a block, and this isn't quite correct, but for right now it'll work. And then here's the alt average array that has all the averaged, smoothed, curved, less entries, and then the R dash line is a red line. Here I label it altimeter in feet and milliseconds here, and I give it a title of rocket. I want a grid shown. I show the plot, and then I close F, and I guess this is closes the file for plotting. And then I save a file, a test PNG, which is the actual plotted data, and I'll show you that here. This is what it looks like, and basically, this altimeter it's only sitting on my table, so it doesn't make any difference. And then here's the altimeter, here's the milliseconds, and it seems like it's correct. I got to double check that, but it looks like it is actually correct. After 10, I think I walked through my house carrying this thing around, and that's basically, I did it for about 70,000 milliseconds, which is 70 seconds, I believe. I think it's 70,000 milliseconds is 70 seconds, and it basically that's 70 seconds, a little over a minute, 10 seconds. So that's basically what I did here, but this is the plot. It's nice and smooth. If you don't smooth it, it gets all jaggedy and you really can't read the file whatsoever. And so that's here we we save that image. If you want to save it, I would save it to a different data folder, because this will try to read that data folder if you run it twice, and it may, in case you run this over and over and over, it'll get corrupted, and it just gives you a bunch of red nasty noise, and it's annoying. And then here he just says, press any key to continue. Well, theoretically, you could have multiple launches. This indicates that you have one launch, and you could have multiple launches. Every time you take the power out here and you put it back in, it's going to create another one of these files and then a bunch of these data files that are greater than 1K. And so it'll create a bunch of these, and you could launch this over and over and over. So you definitely want to see each one of those graphs. This allows you to press a key to input. Then you close F, and then you print done. And that is all this program does. And all in all, it needs a little bit of work. For the most part, it does the minimum. It'll take the data files that you create in your Arduino program, in your Arduino sketch, and this Python module will run it and plot it. You can do a lot more with the plotting, and you can do a lot more, say, with the calculations down here. I just give it a bare bones approach, and for me, that's what worked for this project. So I hope you like this. I hope you share this. Leave comments. I'm not going to comment. I've got other projects coming up that take up too much time, but you're welcome to leave a comment for other subscribers. Please subscribe. Please share. Download the sketches I've written and modify them and use them. I'm fine with that, and I hope you enjoy using the Arduino, the mini micro Arduino with a rocket and model rockets. That's kind of cool to get those two working together. You can do all sorts of other things, and I hope you enjoy this.